So we just discussed undetermined coefficients in annihilation approach. So the undetermined coefficients to try to find that one particular solution for the non-homogeneous linear higher order differential equation. We're talking about constant coefficients specifically in this case. But there are two different approaches. We discussed the superposition approach in 4.4, depending on the form of the function on the right-hand side of the differential equation in the standard form. You can assume the corresponding form of the particular solution, and then with some undetermined coefficients, then you just plug in those forms of particular solutions into the differential equation and solve those coefficients. That's called a superposition approach. In this section, we just use a different approach, annihilation approach. So we introduce the annihilator. Okay, so these are the operators involving powers of the differential operator. You can use some combinations of those differential operators to annihilate the functions in the polynomial form or exponential form, or a combination of them, a product of them, or even for cosine and sine functions. So what's the point of doing this? The point is, when you have a non-homogeneous differential equation to solve, you can apply those annihilators on both sides of the equation, so that you're going to, annihilate the right-hand side the equation. You got some functions on the right-hand side of the original differential equation, but if you apply the annihilators on both sides, then you can, make the right-hand side 0. And then the whole thing just becomes a homogeneous differential equation, because you apply the differential operators. So you only get the equation with 0 on the right-hand side, and then on the left-hand side, they're all, derivatives. So that's a homogeneous differential equation in high order. And we know how to solve a homogeneous differential equation. You just assume the form of the solution as e to the mx. And then you plug it into the new differential equation, the homogeneous differential equation. And then you're going to get the auxiliary equation as we did before. Then you just solve this auxiliary equation, and then you solve the whole equation. Isn't it? Does it make sense? So that's the new approach, all right? So, so this is what I'm saying. So if we want to solve the equation of a non-homogeneous differential equation, L on y equals g of x, so the L is the linear operator. So that involves some derivatives, higher derivatives, okay? And G is a linear combination of those functions, so polynomials, exponentials, and the product of, polynomial, exponential, and cosine sine functions, all of those forms. Okay, so that's the right-hand side of the equation. So this is the higher order linear differential equation we talked about before. We just use the short notation of L for the left-hand side to represent all the derivatives. Okay, so it applies on y. You have some non-zero function gx. Okay, and then the next step, okay, is in this case gx can be eliminated by a differential operator at 1. So that's another differential operator. If you apply at 1 on both sides, you're going to annihilate the right hand side to get 0. Okay, so you apply the differential operator at 1 on both sides of the equation, you get 0 on the right side. So the whole thing is just a homogeneous differential equation. So if you look at the left hand side of L1, apply on L on Y, that's another differential equation because L1 and L are both differential operators. So you just apply them sequentially. You get a lot of differential equation, but now it is homogeneous. That thing that can be solved easily, as we know. Okay. So obviously you want to apply the differential operator at 1 of lowest order, and you don't want to use too much of the derivatives. Okay, as long as we can annihilate the right hand side, that's good enough, right? Okay. So this L1 will consist of all of those products. So d to n, d is the first order derivative. Okay, so d to n essentially means the nth derivative, or d minus alpha to the n. That means you take the derivative and minus the constant to the nth power. So what you do, you just apply d minus r n times. Okay, or you have a form d squared minus 2 alpha d plus alpha beta squared plus beta squared to the n. All right, so again, it just apply this whole thing n times sequentially. So now we can easily solve the homogeneous differential equation by assuming the solution of e to the mx. All right, so let's just do one example by using the new approach, annihilation approach. All right. But this is still undetermined coefficients, all right? Because we still need to determine some constants. So let's try to solve the given differential equation by undetermined coefficients. All right. So this time you're going to solve the whole thing. Okay, not just one particular solution. You're going to solve the whole equation. So first, let's just solve the associated homogeneous differential equation. You just drop the right hand side, put 0 there, and you replace y by e to the mx. So then you get the auxiliary equation for the associated homogeneous equation, or not the original differential equation. I don't know why I wrote the original differential equation, but oh yeah, associated auxiliary equation with the original differential equation. That's right. So then you're going to get a m squared from y double prime and plus 4, because you get 4y here and equals 0. And you can easily solve this equation to get 2 roots plus or minus 2i for m. So then the general solution for the associated homogeneous equation is c1 cosine 2x plus c2 sine 2x. As you know, whenever you have imaginary part in the solution with m, that essentially says these are sine and cosine functions. Okay, but you do have both cosine and sine. Okay. If you have a real part in m, then you're going to have an exponential function times cosine or sine. Okay. But in this case, we don't have any real part for m, so it becomes simple and we only have cosine sine functions. All right. So Now we need to rewrite the original differential equation by operator form. Okay, if we want to use an annihilation approach for undetermined coefficients, the equation has to be written as or in the operator form. So we know the second derivative of y essentially d squared. Okay, and plus 4 times y. So that's the left hand side. And then now we get a focus on say sine x sine 3, sine x minus 8 on the right side of the equation that can be annihilated by a product with two operators, d and d squared minus 2 alpha d plus r squared plus base squared. Then remember we discussed some examples on how to find some operators to annihilate those functions. So you just do it one by one. Okay. So for example, the number 8 can be annihilated by operator d or just this first derivative, because when you take the derivative of a constant, you get 0. Okay. So if you get the polynomial in here, then you have to use the higher order operators or different derivatives. Okay, we discussed those rules last time. But then you have to annihilate 4 cosine x plus 3 sine x, and that has to be done by this operator, d squared minus 2 alpha d plus r squared plus base squared to the n, where alpha equals 0 because you don't have exponential function here, so that means alpha is 0 and beta is 1 because you get the cosine x sine x. Okay, so you don't have 2x or 3x in those trig functions. So beta is just 1. Okay, so that takes care of this, and n is 1. Okay, if you look at those rules, let me see. What do you say? Okay, see the differential operator d squared minus 2 alpha d plus r squared plus beta squared to the n annihilate each of the following functions. Okay, see. So in this case, we got what? Just sine and cosine functions. Okay, so that means what? We only need n equal to 1. Okay, we don't have any polynomial in this function. We just have a cosine sine function on the right hand side. So you don't need this. So n equals 1 basically, and alpha equal to 0. Okay, and beta equal to 1. Just compare the functions we have with those functions, right? Okay. So n equals 1, alpha equal to 0, beta equal to 1. So plugging those in. So what we get is what? Just d squared plus 1. So alpha equal to 0, you don't have this term. That term, beta equals 1, so you get 1 squared, which is 1. So d squared plus 1 to the 1's power. So that's just d squared 1. So we can use basically d times d squared plus 1 to annihilate the right hand side. So if you apply this operator on both sides, you're going to get 0 on the right side, and you have d times d squared times d squared plus 4 operator on y, on the left hand side. Okay, so you still need to apply both operators because you need to annihilate all the terms, and you have to apply them sequentially like that. So now we get a homogeneous differential equation that can be easily solved by plugging in y equal to e to the mx. We know how to solve it. That's always the case. Then we get the auxiliary equation. So if you do that, it just gives you m times m squared plus 1 times m squared plus 4 equal to 0. When you take a derivative, you get the factor of m. So you take the second derivative, you get the factor m squared. Okay, so that's pretty straight. And then you solve this equation, you get m equals 0 or plus minus I or plus minus 2I. You just let each of those factors equal to 0, right? M squared plus 1 equal to 0. So you put 0 to the right, you get m squared equal to -1. And that will give you plus minus I. Or if you let m squared plus 4 equal to 0, you get m squared equal to -4, and that leads to a solutions of plus minus 2I. Okay. So now then we can write down the solution of this homogeneous differential equation. Okay. So what? So that's just C1 plus cosine 2x plus C2 sine 2x coming from 2I. And then C4 cosine x, C3, C5 sine x comes from I. And the constant is C3 comes from 0, e to the alpha x. When alpha equal to 0, you just get a constant. Okay. And that's the solution for this homogeneous differential equation. All right? Remember? Okay. So then what? So now we have to, exclude the solutions of C1 cosine 2x and C2 sine 2x. Okay, because that's the solution from the associated homogeneous differential equation. Okay, so that means the particular solution will be just C3 plus C4 cosine x plus C5 sine x. Okay, this solution here just includes everything. Okay, in the solution of this equation, but that also includes the solution of the associated homogeneous equation. When you solve for d squared plus 4 y equal to 0, that's part of the solution of this new equation. So we have to exclude that to find the particular solution, right? That should not be part of the particular solution because that's part of the general solution of the associated homogeneous equation. Okay. All right. Okay. In other words, this solution, in here includes both the homogeneous differential equation and the solution for that, and the solution for the particular solution of the original non-differential equation, non-homogeneous differential equation. Okay. So that means yp equals C3 plus C4 cosine x plus C5 sine x, as I just said. So what you do now, you just plug in this particular solution into the original differential equation and solve for C3, C4, and C5. Okay. So you can see, you can actually solve the whole equation, in this way, in the annihilation approach. But you have to still distinguish the part of from the associated homogeneous equation and the part from the particular solution. All right. Okay. So now, what else? So plugging yp into this equation, and then that's pretty easy. Just take the second derivative of yp. We know, when you take the derivative of yp, you get 0 from C3, and you get the negative sine x from cosine x, and you get a cosine x from sine x. So okay, we just got a little problem with the board. Let's see what's going on. All right. So you just take the second derivative. So you're gonna get the negative C4 cosine x minus C5 sine x. All right. Take the second derivative, and then plus 4 times yp, so 4 plus C3 plus C4 cosine x plus C5 sine x. That's the left hand side, and it equals 4 cosine x plus 3x sine x minus 8. Okay. So you just combine the like terms on the left and then compare the coefficients of each of all the terms with the right hand side, and we end up with 3 solutions basically. So for example, if you combine negative C4 cosine x with 4 times C4 cosine x, okay, just distribute 4 on the second part, you're going to get 3 times C4 cosine x, and that matches 4 cosine x on the right. So that means 3 C4 equals 4. Okay. Similarly, you can combine negative C5 sine x with 4 C5 sine x. So that just give you 3 C5 sine x, and that has to match 3 sine x. So that means 3 C5 equals 3. And finally, 4 C3 has to match negative 8 on the right. Okay. Then you just solve for the system and get all the constants, undetermined coefficients. So you got C4 equal to 403 from the first equation, C5 equal to 1 from the second equation, and C3 equal to negative 2 from the third equation. So now we solve the coefficients, and then you just plug in those 3 C3, C4, and C5 into the solution. We get the solution or answer for the original differential equation to be C1 cosine 2x plus C2 sine 2x plus 403 cosine x plus sine x minus 2. So that's the final answer. Any questions?